will start with a very short review, because I mean, okay, now we are putting everything together, yes? So now is the important moment. So let's remind ourselves where we stand. So first of all, we began in the UV with the Lagrangian. I mean, we wrote this huge stuff, right? Of pure n equal to 2 super Young mills. And we even said, let's not even do the most general thing because this is too hard. Let's just choose the gauge group to be SU2. And the first thing you are supposed to do, because also we studied monopoles, right? So you need to have vacuum of your scalar potential. And for our theory, the scalar potential was like this. And we found that this has solutions. So for this to be 0, these are the solutions, yes? And we call this Coulomb branch. And once we plug this thing in the Lagrangian, we have spontaneous symmetry breaking. And our SU2 gauge group breaks down to a U1, yes? So after spontaneous symmetry breaking, what happens is that this theory will flow to the IR. To an effective theory of an n equal to 2 photon. Yes? And I said that all these coefficients in the Lagrangian, they are going to be fixed by, they will know all of these things that we integrated out, all of the massive particles that we integrated out. Yes? And in particular, what we get is a sigma model. So actually it's very good that next week you will have these lectures on sigma models because you will appreciate even better what is going on here. So you will have a sigma model with metric. Yes, this is what we had. And maybe I also remind you that this tau of A is the second derivative of this function f, the prepotential that we were getting also with superspace, right? And our homework, like this is what Seiberg-Witten theory does for us, is to compute this. And maybe just a tiny comment to make sure that you are all on board. Of course, when we integrate things out, we are going to have also higher derivative terms, right? These things are not captured by this function. But in the extreme IR, because they scale by higher pairs of the momentum after Fourier transform, they go to 0, so we ignore them. This is what we are doing. Is this clear to everyone? Yes? Okay. Let's wake up, yes? And maybe one other tiny little thing, I don't know if you remember, we said that this A coordinate, because of this vial inside the SU2 gauge, it had this extra symmetry. So we said that the good gauge invariant way to parameterize our Coulomb branch is to use the VEV of gauge, so this is a 2, the VEV of gauge invariant operators. And classically, this starts with A squared. And of course, quantum mechanically, there are corrections. Dot, dot, dot is the quantum corrections. Yes? Are we happy with all of that? Good. So now we were saying that at the weak coupling, we are very happy. We have this description in terms of the variable A. But when we want to go to the strong coupling, something is not good anymore, and we need to find a new coordinate, and we introduce this AD, the dual coordinates, which if you remember also, and I will write it to remind you, they resemble this S duality. So we had this. This one is not stable. Again, if you see something happening, tell me to run, yes? So we introduce this. Hopefully it will not fall on me. So this is what we had. And again, I remind you also that you can form tau of A out of it. DAD, dA, and you can do it also using this equation. So the dual tau is equal to the second derivative of the dual f, and this, because of this minus sign, has a minus sign, and it also turns out to be the 1 over that. So we really here we see as duality. This is what we said last time. This is indeed, doing this coordinate is like doing an S transformation. And again, let me remind you also what else I said, which is very important. So using these coordinates, or you can think of it as a transformation. First, we had that the path integral, and second, the spectrum of dions. Okay. They enjoy as duality, and in fact, not just that. We also said already in the first lecture that this T symmetry, which shifts theta to theta plus 2 pi, this is also automatically a symmetry of the problem. So actually we really have the full SL to Z, yes? And I remember this I did explicitly. This I told you that I could do it explicitly, but there was no point in doing the calculations and killing you. You can read it in Bilal, for example. It's very, actually in all of the reviews, it's very explicit. Yes? And so this is really, we really have this full group, fully at our path integral and fully at the spectrum of the dions. Is this clear to everyone? Fantastic. So now we only need to solve the problem. And we started, actually. And the first stop was the easy one, was looking at the weak coupling. I think the weather today is affecting the mood. Everyone is very tired or something, you know? What is going on? Now is your chance to ask questions. So we will do weak coupling for a second, I will remind you. And then we will go to the strong coupling. Yes? So we had, yes? No question. So first of all, I wrote this equation. And we said that this is something you can obtain by a Coleman-Weinberg type of calculation. And then all we did is we took derivatives of that. Yes, so we wrote AD. Yes, and okay, in a moment I will write A. So one of the things that I did is that because we are in the weak coupling, we can say that U is A squared and forget about the dots. So we write this. Okay, you can plug in, and here the same thing. And by doing this, we go to now the U plane. Is what I'm drawing visible all the way to the back? Yes? Actually, this is also review, but... And also, if someone was not here last time, it's really now a good opportunity to ask questions. So here is around u is equal to 0, and this is the strong coupling. Regime, and here, far away to infinity, this is the weak coupling. Weak, yes, all of this. Yes? So what we did a monodromy around infinity. And we got this matrix. And we also said that this matrix can be written in terms of the T transformation, and this is really a nice SL2Z matrix. Is there any question about this? Was this all very clear and nice? Fantastic. Then the next question was, great, so these are multi-valued functions on the U-plane, and we need to see the branch cut that comes out of infinity, where does it go? And we started asking the question, how many singularities there are, right? And the first thing we said, is it possible that there are two singularities? And maybe I can quiz you. Why there are not two singularities? Do you remember? Can someone tell me from last time what happened? And you remember something, yes? So we had two things that we said. We are calculating this metric, right? And the metric comes from this f, and the f is a holomorphic or meromorphic function, right? And because this guy is holomorphic, okay, I will write it. Okay, these are important things. My quiz failed. So, two singularities, the answer is a no, and the y is so what we took as the simplest example. Okay, I write this and then I explain why. So we took infinity and 0. So what we said is that this function should have no other singularities other than these two, if this is the case. But remember, the f is equal to 0. So this guy is a harmonic function. And we also said that our beautiful metric, which is obtained by this guy, has to be positive definite. And basically what we said that these two guys are not compatible. They are only compatible if tau is a constant. Yes? And this is what you said. For n equal to 4 super young mills, this is correct. Tau is allowed to be tau is a constant, and that's great. But if we are studying an n equal to 2 theory, we have a non-zero beta function. So this cannot be a solution. So this assumption is wrong. Yes? By the way, this is what we had. Why did I put 0 here? I remind you, I had this argument that all singularities, of course other than 0 and infinity, they always have to come in pairs. Do you remember this? Very good. Why? Because of the U1R symmetry, right? So we said that phi, our friend, to whom we give the vev, has U1R symmetry in some conventions plus 2, but this is really convention, so it really doesn't matter. We said that this beautiful U1 breaks, I don't remember, someone said it, sorry?
This U1 is broken to some Z2 symmetry, so that's...
So it's broken to a Z4 by quantum effects, instantons, and one loop, yes? But then when we form U has a Z2 because we square. So because of this, all singularities have to always come to in pairs, yes? And this is why when we wanted to study the simplest possible example with only two singularities, we had to put this, we know that we have it, we had to put the second one at infinity, yes? So that is it. So, and this doesn't work, so we move on to the next option, yes? What's the next option after 2? 3, yes? So let's do 3 singularities. And this will be the real deal. This will be the way to do this. So we will have 1 at infinity, because this is the weak coupling. And then we will have 2 more at some place U0. We don't know right now what it is. And honestly, it doesn't really matter. Yes? So let's go along with this now. Now, okay, also I said, last time I said that one of the magic about being Seiberg and Witten is that they wrote down this, you know, AD equals, this Legendre transform type of thing. There is a second magic about being Seiberg and Witten, and this is what will happen now. And I really want you to learn this. So I will write a sentence in a moment. So what happens, but I want to try to say it in a way that you will never forget. So if you have a singularity, the metric blows up in your face, yes? This is what happens. Things never blow up in your face unless you did something bad. What is that in an effective field theory point of view? It means that you integrated out particles that are massless, and you shouldn't have done that. Is this making sense what I am saying? Singularity means that there are massless degrees of freedom there that you illegally kicked out. So let's write like, okay, so this is my way to say that you will never forget. I will write now a human sentence. We get singularities. And by the way, whatever you will study in your life, Seiberg duality, all of these things, this line is the most, this is effective field theory. You really need to know that. There is no life without that, yes? So we get singularities in the metric of moduli spaces. When particles become massless. Yes, this is very, very, very important. And of course, Seiberg and Witten used this. How how are we going to use this? So you remember in the first lecture, I wrote the mass of the monopole, and I wrote, oh, this is very heavy, and someone even complained. And then we had to say that in life we live, you know, the coupling constant of in electromagnetism is very weak. So this is why the monopole is very heavy. Yes, I was comparing it. Yes, very good. So this is what happens in the weak coupling. The monopole is very heavy. What if we extrapolate that formula is going to happen in the strong coupling? The mass of the monopole will do what? It will go to 0. So we say that the monopole has 0 mass. This is what we want to study. Yes? So, fantastic. And this is, in some sense, like, this is the way in. Like, okay, this takes a genius to say this and start. I mean, the way I present it, it sounds very simple, but, you know, yeah, anyway. This is the way in. Remember, we also wrote the M for the magnetic monopole. And in one of the formulations that we wrote it, first of all, we were writing in general that M can be written as AN plus ADM. You remember this formula? So for a magnetic monopole, this goes, and I have only this, and I put M is equal to 1, so it's basically AD, yes? So when a magnetic monopole is massless, a magnetic monopole is massless when AD is equal to 0. Yes? You want to ask a question?
I mean, I don't see why you say that it has to be magnetic monopole.
It doesn't have to be, but we are doing magic and we are trying to find our way in. And in fact, you do not have to say that the magnetic monopole is massless. You could choose your favorite dione and say, let's make it massless and see what happens. The answer is you will get the same physics up to reparametrizations. So this is the simplest way in. Sorry?
Is it clear that it has to be a dione?
We have nothing else in this life. So in this life, we have integrated everything out. And the only thing we have is our BPS particles. We have the spectrum of this and nothing else. Yes. So, and this is the simplest thing we can start with. Again, you could start with a dione, you would just make your calculations harder. So let's just start with this. Yes? Yes, this is a fantastic question to ask. Why do we do that? So, this is very good. I will write two equations here for A and AD in terms of the dual variables that I will prove in a moment, but let me write them first, and let's talk about them a little bit. Yes? So they are to be proved. They are just for now. I call them also a name so that I will recall them later. And you can see, basically, I just wrote, so this is a stupid line from the board. This is a minus, yes? U minus U naught is the place, is the place where we are looking, and it goes to 0, yes? So this is around U. This is what we are trying to do. And this, okay, it shouldn't look crazy to you, but we will prove it in a minute, yes? So, and also here I have some coefficients, which at this moment, we will see, we don't even care to fix them, actually we will rescale them away. Yes? Now, let's play our game, and maybe I already say this, we will rescale, and we will see that we are allowed to do this and it doesn't matter, and we will place our u0 to lambda squared, because actually the only scale we have in the problem is this. And because we have two of them, there will be the plus lambda squared and the minus lambda squared, and there is nothing really else. So we will just rescale to that. So let's do this, and let's do the same trick, what we did before in the weak coupling. Let's do a monodromy. Around this u equal to u0 is equal to this lambda squared. So what happens? I will use these equations that I will prove again. I will prove them in a moment. And this is what I get. I don't do again super explicitly like last time the calculation, because the calculation is basically identical. Again, we will write it like a matrix, and this matrix is equal to this. Yes? And this matrix, again, like in the weak coupling, but in a slightly different way, it can be written as S and T transformations, and it belongs in the SL to Z. So this is good. We keep doing good things in this life. Yes? Now I will do a cool observation, because it is cool and it's useful also. So note the following. We have written this already, but let's write it again. We have written this equation, and we also said that this is invariant under SL to Z. We talked about it, and we also said that maybe a nice way to, so we can think that we have this type of inner product. Yes? So where these guys transform with M from the left, and then I could think that then M transforms these guys from the right. Now, if I write down this matrix, M, yes, I just give it to you. First of all, what is the determinant of this matrix? Yes. So this is a nice matrix. And because of all these integers, it belongs in our favorite group, right? Let's do also something else that is very cool about him. So let's take this matrix and multiply our dione pair. What happens? Okay, I will let you do this at home, or maybe you can do it super quickly. You get back the same. Basically, very beautifully, this plus and this minus, and also this minus, they are like at the right place so that they cancel. So this is very good. Why this is very good? Because we discovered a matrix that leaves invariant the pair, the dione. Yes? Any dione. But still, this is an SL to Z. Yes? So we can interpret, okay, of course, you can tell me, oh, Elli, you were just very lucky, but I am consistently lucky, and I will tell you in a second. So for the weak coupling calculation that we did, this M infinity, what happened there? This was an Mn matrix with M is equal to 0 and N1. And also the matrix that I wrote here, this is an M01. So what happened here? In the weak coupling, my monodromy is the one that leaves the electron invariant. And in the strong coupling, this matrix that I discovered is the one that leaves the monopole invariant. You can take it as a very cool observation, but you know. My PhD advisor was always telling me that luck comes with the people that try. So if you don't try, you will never get luck. Anyway, I don't know if you can connect the points, but. So we are almost there. We have almost everything. This I will prove. Okay, I delete it. You have it in your papers, yes? I will prove it in a second, but maybe we don't need to have it. So we have everything. We have M infinity. We have the one of the strong coupling monodromies. And the second one we will calculate by this equation, yes? Which we already wrote last time, by consistency on the U-plane. And we write it. What is the answer? So this is the answer, and you can write it also very nicely. Like this. Yes?
How do you determine the order of the product of?
This is a calculation. You just calculate. Yes? You just plug in. Here, I have written M infinity in terms of minus, so M infinity is minus t to the minus 2. I wrote this guy in terms of some whatever, what it was, s t squared s minus 1. And I plug everything in and I calculate. Yes, this was, yes, and I get this. So this is an SL to Z, also very good. Oh, and I have this beautiful thing with numbers, and I compare, and what do I get? I get something very nice. I get that this is the dione that is left invariant after this matrix. So you see, my happiness persists. Yes? Again, this is a cool observation. Anyway, and there is another cool thing about these equations, which is written here. So what do we see is that the monodromy around the second strong coupling point is a similarity to the transformation of the other strong coupling monodromy. So, you know, this is nice. This you can see as a, oh, it's consistent. We have the u and the minus u, and they should always be together. And like this similarity transformation is a manifestation of that. Yes? Are we happy with all of this? Yes, please ask.
Does this prevail when I were to like kind of shift the meanings of all of them around? If I were to go to u0 and then try to interpret 0 and minus u0 as my new pair of doubles. Can I like, I don't know, can I exchange the 3 points in their meanings? Just through order?
Sorry, can you ask again? So you are asking if you can just exchange the points and that it doesn't matter?
It feels like 0 and u0 are kind of nice because they're like 1, 0, 0, 1.
Sorry, what is 0?
Well, you've got 3 singularities, right?
So we already said that, yes. So we have the one at infinity. So this is the one.
Well, yes, okay.
Okay, so not 0, infinity.
Yeah,
okay, so infinity, and then there are 2 others, the plus something and the minus something. And the answer is it doesn't matter where they are actually. You can always rescale and, you know, put them basically wherever you want, as long as the one is minus the other.
Okay.
This was the question?
Turn them around.
Turn them as much as you like. Basically, what we are doing now is at the complex plane, and as long as this, you know, as long as this equation holds, so it's topological. It doesn't matter where they are. Basically, that's the only thing that matters in this life. And I really didn't really use the position of this. Like I never really used it. I just called it that just because this is the only scale we have in the problem. And in fact, you can also set it to 1 and nothing happens. Yes? Are there other such questions? This is important.
So at the end, we are not free to choose the position of the points where we want. But
You are free.
Can you take a limit where they collide? Because then it would be.
Yes, but what we want is that lambda, if you collide them, is like sending lambda to 0. So you destroy your effective theory then. Effective theories are defined by a lambda, right? So it's important to have it. And strong and weak coupling are always defined with respect to this other scale. So you need this scale in order to do anything. Good, now I will derive these equations that were there. So, how do we do this? Again, we think physically. So now we are in the weak, now we are in the strong coupling. The monopole is massless, and we need to go to the dual degrees of freedom. Yes? And maybe I remind you, strong coupling is this. So there, what we will have is a dual photon By the way, I don't know if you are okay with this, but always when I write n equal to 2 photon, I mean the full n equal to 2 vector multiplet, you know, under U1. Yes, this is what I mean. So we have a dual n equal to 2 photon, which is now weakly interacting. Because we did our SL to Z with, so now the magnetic monopole, I can think of it as a dual electron. Yes? This is the setup. Yes?
Is it obvious that a much smaller than lambda
Yeah, you have to plug in the equations. Yes. Nothing is obvious. You have to plug in.
But this is all the Lagrangian, non-projectively.
Yes. So this is a very good question. So first of all, you can plug in the equations we already have at weak coupling. And then you can wait, solve the problem, and test what I'm telling you. So whatever I am telling you is if you wish, very intelligent assumptions that these very intelligent people made. And then we will have a solution that is exact, and we can test everything. So that's the correct answer. So now we have a dual weakly coupled electromagnetism. And our monopole now is like the dual electron. So what do we have? We have dual n equal to 2 super QED. And we can calculate the beta function of this guy. This is very easy. I just write the answer. Again, this is n equal to 2 super QED. And I had a disaster, I was not writing this too, but anyway, this is the correct formula now. And again, tau, for now I forget about the theta. So you should always check my equations, this is why I said this. So this is what we have. Yes? And also again, because we are thinking like the same way up to the way we are thinking up to now, our scale of the problem will be the dual A, because now we are doing everything in dual. And basically that's almost it. We can just plug in. So this is the equation for the beta function for tau, where I have also, used this. Yes? And now I don't do anything, I just do the integral, let's say. Yes? And now I remember.
Is your mu as lambda?
Sorry?
Is the mu?
No. Lambda, we are doing effective field theory. Lambda is the scale of the effective field theory. Mu can move. Yes? That's the point. And we always compare mu with lambda. That's why, yes? Yes. I mean, okay, I understand that the biggest struggle in terms of, also when I teach, like it's the same, effective field theory is the hardest thing for people to get. Yes, but okay, yes, ask, please ask. Yes, good. Good. And please check my coefficients, especially when I copy, maybe something will be forgotten. So we had also this, yes, we also had this equation, and then we just combined them. Oh no, this is A. Some constant that I don't care about. And this is almost the equation, right? Almost. The only difference is that here I had u minus u naught. Yes? So, as a function of u. Yes? But again, first of all, we remember this was the point where the monopole becomes massless. So we clearly want something like, maybe a coefficient. We don't care about coefficients. We clearly want something like this, yes? And the only thing we don't know is, again, the coefficient doesn't matter, this power. How do we find this power? We ask that this is consistent with our happy SL2Z. And actually, it's even faster if you compare and you ask that this is consistent with these nice matrices with the integers that I wrote that live invariant, the dions and the monopoles and all of that. If you do that, you fix P to be 1. Maybe I write a sentence. If you demand and even more. Are we happy? So I just derived for you these equations that I promised I will derive. Yes? Are we happy? Is this all making sense?
Yeah, so there's remaining unknown. You had a C0 in your formula.
Yes, so it is there, it's there. I will never care about it. Let it be C0. Yes. It really doesn't do anything, yes. And you should not believe me, you should check me. Yes. I mean, anyway, in a moment, or not in a moment, but in some moments, I will write down the solution and we will check. So, what I just did, I finished all the physics. So there is no more physics now. So we made all of these very clever, I mean, we followed the masters, we made all these very clever assumptions, and we set up a problem. We set up a problem where we have these functions a and ad as a function of u, yes? They are multi-valued. We know that there are 3 singularities at infinity and 2 other points plus and minus. And we know precisely the monodromies. And now we need to find a way to solve this. This is now a math problem. We need to find a way to solve it. So I would say maybe we can ask maybe a question or two now, and then we make a break, and then we do the math. Yes.
Relevance to the specific dion 1 minus 1 that sits in the hole.
So none of this matters. And in fact, what you can do is you can say, I will not start with a monopole. I will start with my favorite dion n, m. Find the singularity, like find the monodromy, and then find the other monodromy, and this is some other crazy dion, and the solution is always the same, basically.
This seems to be like a global shift. Can you also shift like individual ones?
What do you mean by
Like,
individual
I
ones?
think 2 are going to be 1, 0, 0, 1. The third one is specified to be 1 minus 1, or can I like? Is there a way to like shift the
Basically, when you shift the dions, so the dions, because of this structure Na plus Mad, they live in a torus, they live on a lattice, and by making different choices, you basically start describing this lattice from a different point. But who cares? It doesn't matter. But again, at this moment, these things are all assumptions, and when we have the solution, we can check what I am saying. Okay, let's now have the break, and we come back and we do the math. Okay, so again, we are done with physics. You are very welcome to ask questions. And if not, I mean, anyway, we can also talk more over pizza and stuff. But again, we made our assumptions, we phrased the problem, and now we want to solve it. So let's first state clearly the math problem we want to solve, yes? So we have AD and A. And these are multi-valued function on the Ur plane, or maybe I can say that they are single-valued apart from the on the U plane. The 3 points and the plus and the minus, lambda squared, where we know the monodromies. We have calculated them. This is the math problem. And this is a famous problem in complex analysis. It's called the Riemann-Hilbert problem. And what's important for us is that it has a unique solution. So if we find one, we will be very happy because that will be it. Yes? And maybe I should say, okay, so I expect that most probably most of you will have never seen this. Unless you took a very nice mathematical physics course or an advanced complex analysis course, most probably you will feel unhappy. But we will go easy and slow. But maybe let me say that, I mean, especially at the time when Seiberg and Witten did this, but also now, this problem, this Riemann-Hilbert problem, appears everywhere in physics, and with emphasis on integrable models and 2D CFTs. Yes? So this thing existed, so these guys basically recognized it. Yes? And maybe I will just say in words, there are two ways. Of course, one shouldn't say that they are two ways, because in some sense it's all one. But stupidly, there are two ways in. One way is to recognize these objects as solutions of a differential equation. And this is something you know, like from your quantum mechanics, you know how to do these things. So these are solutions of a differential equation. The special thing about them is that this differential equation has regular singular points. If you don't know what this means, it doesn't matter. The hypergeometric differential equation has this. Yes? So this is what happens, and you can follow this path to the solution of the problem. And I am not going to do this today, but I really encourage you to read this. So from the references that I gave, there is the one by Bilal. He does it like this. Yes? He follows a differential equation path. And it is a very important path to follow.
Where does that differential equation come from physically in the application?
Read, because it would take too much now to... I will describe the other way, and they are really one-to-one, but if I would try to, it would take too long. So now there is the second way in, and the second way in is that we will recognize these things as periods of integrals of an auxiliary spectral curve. Yes? And this is what Seiberg and Witten did. And the reason why this method is cool and I will follow, first of all, I will just follow because this is what they did and we are doing what they did, so that's it. But also this is very nice because it is very easy to generalize this to higher groups, to other cases, and generalizing this becomes like it's just geometric, and so you can just do it in a very visual way, and I really like that. And also what I really like, we will not do this, but you should really read about this and you can ask me over pizza. This auxiliary curve that we will pull out of the hat now. Also, when you study string theory, actually, in string theory, this auxiliary curve exists. And you can look at it. It's an M2 brain, whatever. Anyway, M5 brain, anyway, ask me, yes, over pizza. So this is a very nice way in. But again, both of the ways, in some sense, when you know enough math, there are no two ways, there is one way. Yes, I'm just saying all these words. So read Bilal for your education, but now we will just follow Seiberg and Witten. And another thing, to appeal to maybe your advanced course in complex analysis so that it's not too freaky, I want to give you a typical example of something like that. At least, you know, if you would ask me before I studied this, if I had ever seen anything like it, yes, it was in my advanced complex analysis course, and it was like this. So if you take a function f, and I already write everything as a function of u because we are in the u plane, and this function looks like this. And this f is a hypergeometric function, and maybe I should actually write down the hypergeometric function because this is good for you and for me, I guess. There is a normalization. Sorry, this is gamma. So gamma is the gamma function, that is the generalization of the factorial to the complex plane, yes? This is X. This is in Wikipedia. I just copied this from Wikipedia, yes? Nothing fancy, or from your favorite complex analysis book. So this function here is a function of u, and it has singularities, of course because of the square root, but also because of the hypergeometric function. At 0, 1, and infinity. And the point is, you are allowed to play with u on this complex plane and go around. And once you do this, this function will mix with another function that I will write in a second. And this is how you, yeah, okay, you are not, yes. So this is the first time, maybe you have seen this for the first time in your life in some nice complex analysis class. Yes? So, and by the way, this is why in some sense it's the same with the differential equation. The differential equations always have the two solutions, and you have to fix the asymptotics and all of that. So this is how these things work. So now some other power, not the square root. And again, this hypergeometric, but with, you know, the ABC, they are, you know, prime, they are different ones. Yes? So this is most probably what you have seen in your life. Who has seen this? Can you raise your hand? Okay, it's not very bad. Okay, so I was good to pick this example. So this is actually the solution to the problem will be that roughly this for a solution for a choice of ABC will be the A, and this for a choice of ABC prime, it will be the D. So in some sense, I have the solution already for you. But yeah, let's now do it systematically. So we had this SL to Z, yes? And the SL to Z, I mean, and we said the word torus already many times, right? So let's now write an equation that describes a torus. And of course I am parameterizing my equation already with my nice parameters, yes? So forgive me, or just accept it. By the way, if you would just want to describe a generic torus, you would write something like this. This would be a generic equation for a torus with whatever parametrization you like, and I just fixed my e's to be the ones that I like, to be the plus, minus, the u, and the infinity. These are the parameters I have in my game. Yes? Now, why this is describing a torus? Let's first understand this in a very visual way. This is very easy. If it's not visual, I don't like it in general, so let's do this. So why this is a torus? Let's take the square root, yes? We have y is equal to plus or minus this whatever square root thingy here, yes? So what we have is that we have two sheets. So this is one, and this is another. And the plus lives here, and the minus lives here. Yes? Are we happy about that? Now, each sheet has zeros, branch points. So, maybe I write. What did I do?
So you have x minus e4.
So, yes, what I said, this is the most generic way to describe a torus. And you can understand it. If you want to describe a torus, you need a parallelogram, right? So you can, I mean, we need 4 coordinates. Yes? And what I did is that I rescaled one of them to go to infinity, so it dropped. And then I rescaled y. This is always the name of the game. So I have my branch points, and I can draw them on my beautiful or not beautiful picture. So 1, 2, 3, 4. Yes? And I will just assign them now. It really doesn't matter where I assign. So let's put the minus lambda squared here. Is this visible or I'm squeezing things? And the infinity here. This is my guys. Yes? And now I can draw my cats, and it doesn't matter. I can choose where to draw my cats. Let me just draw them wherever I like. Yes? Now it's becoming more like a torus. Yes, how do you see the torus? Is this a torus in the head of everyone? No? Where is the torus? So we take the y is equal to plus the square root solution. This is the u-plane one. And we can think of it as a sphere. We take the second guy, the y is equal to minus, and we can think of it as a sphere. This is what you learn in the topology, maybe class. And each branch cut corresponds to tubes. Boop. Is this a torus? Yeah! Yes? And we can make colors now. So, what is very important in this life now, it will be the A cycle and the B cycle. Let's make it. So this, we will call it A cycle. Okay, I'm squeezing a little bit things, but with the color hopefully is visible. And by the way, this is also equivalent to this, yes? Because, you know, deforming this to go to that. I mean, in the torus picture, you can see it beautifully. Deforming this, it can go here, yes? So this is equivalent, eh?
The inverse.
Yes, 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 but okay, up to a minus, it's the same, yes? Amazing. And we have another cycle that I will make with another color. Maybe we can make a pottery happiness like this. And this is this one. Yes, and this we will call the B cycle. Yes? And by the way I am choosing them, it really doesn't matter. It's just a choice of a basis. And in fact, our happy SL to Z, it will take the A cycle and the B cycle, and it will map it with a monodromy to the A and to the B, a new one. Yes? So it really doesn't matter. It's just a choice of drawing things nicely, as clearly as possible. And maybe, okay, I delete this. Okay, the hypergeometric functions will come back to you. With great emphasis on this beautiful equation, yes? This equation is actually a true equation when the B and the C, the real part is positive, and the way I wrote it, I think the real part of C is bigger than the real part anyway, but you can check Wikipedia. It's all from Wikipedia. Or ChatGPT. You can ask, can you tell me how to solve the Riemann-Hilbert problem? Can you give me an example? Good. So maybe a comment, because it will become important very quickly, because we want to check all of this madness. So we have our torus, and we can do things to it to degenerate it. Yes? So when there are we can send u to infinity. So here is u, here is infinity, they go close. And this way I shrink the A cycle. What else can I do? By the way, you are noting that this is my weak coupling. Okay, I'm not solving anything yet, but I am reminding you. So all of the operations that we are allowed to do on our torus, they correspond to physics, what we already did. We can send u to lambda squared. Yes, here I get a 0. And you can see here what happens. Clack, the B cycle that generates. So this is some strong coupling. And of course you can also send it to the minus, and you get a linear combination. Yes? Is this all very visual and nice? Yes, please.
What is the coupling at u equals minus lambda squared? Do I expect it to
So you should do S duality, yes, and then you find it.
So it should be strong.
Yes, it's strong, it's strong, it's strong.
Is it just really by t?
It is related. Actually, okay, we have to, a little bit, yeah. Okay, could we continue? Maybe because I want to keep this picture, let's keep this picture as long as possible. I will delete this. You wrote it down, yes? So now we want to talk about the tau, the modulus of the torus. So this is input. Like, if you don't know this, you don't know this. But the input is that you can obtain it as the ratio of two periods of the holomorphic one form. I go under. This is Weierstrass. Yes, so this is the holomorphic one form. Omega is the A cycle integral of that. And omega D is the B cycle integral of that. And when I say y, I mean take this equation, yes, and plug in and do the integral. Yes? Now, if someone here is used to these integrals, you can immediately see that because if I plug this in there, the monodromies of this integral actually are precisely the ones we wrote down. But I don't expect that you are used, so we will, like a sample calculation is going to come, yes? But if, you know, Seiberg and Witten, when they were doing this, they were used to this type of integrals, so they could see the monodromies in front of them. Maybe I just write a comment. Yes, if you cannot see it, it doesn't matter, we will calculate. Okay, so now to finish this job, we need to identify this mathy thingy to a more physicsy, like to the precise problem we have. And without deleting everything, I will try to keep as much as I can. Okay, the torus I will delete, it's in your mind, yes? And Adav will make a pot. And this we delete. So, the tau of u that I just wrote there, of the torus, of the mathematical problem, we will identify it with the tau of A we want to compute, of the gauge theory. From the gauge theory side, we already wrote this. And now we will write it even a little bit better. In fact, there was a moment that you could have complained to me when I told you that this is a duality, but nobody did. But now, after this equation that I will write now, nobody can ever complain to me anymore. So this will be our friend. And this has to be equal to this, omega d over omega. So I identify them. And also, you should note that, you know, if you compare this with what we were doing before, there is only this stupid u there with the derivative. So the monodromies of this problem are identical with the monodromies of the problem we were doing. Yes. So we are almost done because I mean, you can say that that's it, but let's just integrate the u so that we write A equal and AD equal. Okay, now this will go away, yes? Is everyone good? So, integrate in u, and we get A. Okay, so this is now the Seiberg-Witten differential. I will write what it is. And you get AD is the B-cycle integral of the Seiberg-Witten differential. I'm using these equations, yes? You can think that you take this equation and you take a derivative and then you land there. Yes? Yes? And maybe now I should write. Because now I see explicitly the u, and I will do my integration. And this integration constant, or whatever exact form, this is something you will always have this ambiguity. and you will fix it just by going to things where you know the solution, how it should look like, for example, in the weak coupling, yes? So that's it. Basically, we have now if you believe all of these things that I have been saying, we have the solution. Are you happy with what I have been saying? This is important. Because if you are happy, I will write the solution.
Here, the A, they depend on lambda, right? And
So lambda is this lambda Seiberg-Witten, and this lambda is explicitly this.
I mean capital lambda, right? At the beginning, when we were dealing with parallelograms, we said the position doesn't matter, but here it does matter.
Yes, but if you rescale x, you can, push lambda around. And also, that's the point of all of this. We will fix so that the things we know, like the one loop result, is the one that we know. And we know where lambda is in this one loop result. Remember, we had the log of a squared divided by lambda squared, and we want the lambda squared to be there. So we know where we want it to be. Yes, please complain, basically. Now is a very good moment to complain.
I'm missing a factor 2.
How? A factor of 2. Maybe I made a very bad thing.
Integrating 1 over square root x minus e.
Okay, maybe you are right, but I don't want to put it because maybe I ate it somewhere. So you have to check me. Yes? Yes. I know what you're talking about. I don't know what I did with it. It's gone. Actually, I know what I did about it. I have rescaled everything with this factor, and let me tell you where it is. I am super sneaky. I had this u, and today I introduced a second half that went here. So I rescaled u by this half. This is what happened. And of course, then I rescaled everything, because I didn't want to have factors nowhere. Can you see? I said that u is not trace phi squared, but 1/2 phi squared. So the one u from the other, they differ by a half, and in fact, then not only the u, also the x, everyone. Okay, so now we write the answer. So the answer is a of u is equal. And again, also these factors, we put them so that the one loop thing, the weak coupling solution that we want to get the right one, because here we only have a well-defined the ratio of them. So we could choose whatever we want relative, yes? And in fact, it took me a little bit of time to get my act right. I think I got it right, but you should check. So I just plug in. So this is the one, and this is the other. And by the way, sorry, maybe I should go slower. What is this integral? This is the A integral, right? So I am making my contour, right? Hug very carefully this, yes, interval. This is what I'm doing, yes? And this is the B integral, so I am going here. I'm making it go. There is a dx somewhere. So this is the solution. Again, up to coefficients that I chose so that the limits that I know are the correct one. And if you don't like that, put some coefficient alpha beta and fix it in the end. Yes? Questions? Also, I will delete our beautiful Seiberg-Witten differential and I will write here. This is blasphemy, but it's okay. If you wrote down on your notes the hypergeometric function in terms of the integral with a, b, and c, you can also write it down. And this, the first one, is square root. And here you see this is 1, yes? And here there is an I. By the way, here crucially, this 1/2 that I put here, if you didn't have that, you would have a square root of 2 here, and also this would be in the numerator. So I did a little bit of happiness so that I don't have the 2's, at least in the places where I don't like them. Of course, yeah, it doesn't matter. You know what I'm saying. Okay, I'm squeezing things, sorry. So this is this. So this is the solution to our problem. And now we need to check it a little bit. Yes? And checking it a little bit becomes either an exercise in expanding hypergeometric functions, but honestly, the best way that becomes the most intuitive, and you can do it almost without mathematics. I mean, you can do it with 0 Mathematica if you are quick with integrals, or with a little bit of Mathematica if you are a little bit slower with integrals, is this. And in fact, this is the way I always do it. So in some sense, for me, this is nothing. It's just a fancy name, but I can calculate here. Yes? And the way I calculate here is that I shrink these cycles the way we said before. So let's do a little bit of a sample calculation. But in some sense, the problem is solved. Now we will just check it, yes, that we are not crazy. And also that all the little factors and all the little happiness that I did, it's all okay. And by the way, for explicit calculations, like what I will do now, okay, in no review, it's completely explicit. So, you know, I did it. But Tachikawa has a nice, he shows you how to do the weak coupling, and this is very nice. And also there is another very nice review, and this is nice for many reasons, so I will also write it here, by Hocker and Fong, because this I didn't cite when I gave the abstract. And the number is 991227. So this has, like, not all the way explicit, but it has calculations. So this is nice also to have something. Yes? Okay, so let's do some checks. And the full set of checks that you can do is basically three things. The one is send u to infinity and get what we had. Second, send u to lambda squared and get what we had. Yes? And third, and maybe the third, because it's more, I did it with Mathematica, I will just tell you what is the answer and then I will start showing you more. So the third is, remember yourself that tau of u, remind yourself, is this, dA du. So take what we wrote there, write it in Mathematica, do the derivative, yes, or take the formula before, so anyway you have it without the derivative. And then in the weak coupling, ask Mathematica to expand. So and what is weak coupling? Is u is much bigger than lambda squared. Yes? And by the way, here, if you want to do the calculation the fastest possible way, you set lambda is equal to 1. So there are no lambdas, you know, because otherwise it's really a pain to do it. And then wherever there is a u, because u is it has a, you know, mass dimension, afterwards you reintroduce lambda appropriately and you get the right thing. So if you do this in Mathematica with this over this, with derivatives, you get something super nice. You get precisely an equation that I wrote last time. So this is the third check. I will do the first and the second in a moment. This equation I wrote last time, and I told you that if we have time, I will derive it for you. It clearly is not going to happen, but I have here the derivation, so we can do it while eating pizza. And you just need n equal to 1 supersymmetry and holomorphy arguments to do this. It's very easy. But this equation is very, and people like Seiberg and Witten knew this equation before they did their work. Why this equation is amazing? It has the one loop result that we studied, but it also has all the instantons. So this is a proper, the instanton expansion. And remember what I told you last time. This is a 4, yes? So this is why this is an instanton expansion. Yes? The 1 over g Young-Mills is here, squared. Yes? And so when you do your holomorphicity Seibergology type of arguments, you get this form apart from these coefficients. And the solution, doing the integral, gives you these numbers. Yes, so this is amazing, and you can expand with your Mathematica and get all of these numbers and be very happy that you solved the problem. Yes? So this is the one check. Now let's do check number 1. Yes? I will do for sure check number 1, and it depends on how fast I write. I will maybe also do check number 2. Okay, it doesn't matter. Are there questions?
Is it possible that we have more than 3 singularities on the
let's save this question for the end, because now it takes me away from what I am doing. You can ask this question, and this is a very legitimate question, and you should definitely ask it. And the question is that you will get things that are not consistent with what we are doing. This is the answer, sorry.
Yeah, since it seems that those method of those curves only works for...
Again, this is true for this SU2 theory that we are doing, yes? So if you do something more crazy, you will get other stuff. Yes? So now we are doing a very specific, we do pure Young Mills, nothing else.
Are these proof like the CL, it's like some rational things, like...
Now, yeah, they are some simple numbers, some whatever, yeah, 1 over, I don't know, blah, 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 like, yeah, numbers, like, yeah, rational, like, beautiful numbers. Yes, yes, yes. Okay, so now we do check number 1. And, you know, you open your notes where I had the weak coupling, and if it's wrong, you complain, yes? Good. Again, up to my ability to get the factor. I think, I mean, I did some serious effort to get the factors right. So this is what we have from the Seiberg-Witten curve. In a moment, I will write the other one down, but let's do this one first. So we have u going to infinity. So you just look here. Basically, you have to drop x, right? So what happens to this guy? And there is a minus. Very crucially, I was missing the minus. You get an I. Yes? And the rest, either you do it by yourself, the integral, or you ask Mathematica to do it for you. The answer of this integral is basically, maybe I just write it here. But you know, everything, what is amazing is that it works with factors, with everything. So this is this integral. Or you can recall your beautiful high school. This is precisely minus I pi. It's amazing that it works, but it does. And really you get here this. And this is correct. Yeah. Yes? Now let's do the other one. Again, this is the B-cycle integral, and to get it, you make. Anyway, we talked about it. How you get this? To the 4th power. So now, what you need to do in order to achieve this integral is you need to do a rescaling, and you can define, let's say, y is equal to x divided by u. Yes? So what will happen? Is it okay if I write on the top of this? Okay, this is not so nice, but... So this is what will happen here. This will become 1. There will be factors from here and from here that I have to pull out. So what is going to happen is that I will have square root of u over pi, and then I will have this integral. This is what I have. Here again, I'm using, once I am doing my rescaling, I'm using the fact that u goes to infinity, yes? And this integral just by itself is equal to I ln, and I am thinking that this is an epsilon, a small parameter. So this is what I told. This is this. So then you collect the factors and you get precisely what we had. At least to leading order. So I am thinking that this is a small parameter. Which is the correct answer? Yes? Did I give you a little bit of an idea for how to do these things? What is the time? So look, we have 4 minutes or whatever. I can do for you if you want the second, or I can just say some words to end nicely. What do you prefer? Let's say some words. But what I want to insist, okay, I am being very nerdy, and you can also maybe look at my notes. It is very impressive how these things come out. They are meant to be. Are there any questions, first of all? Maybe this is the most important thing. Maybe let's recap the magic. So we started with the theory with SU2 gauge group, okay, n equal to 2 supersymmetry, whatever. We found the supersymmetric vacua, we plugged in, we had spontaneous symmetry breaking, we allowed flow to the IR, and we have an effective Lagrangian of n equal to 2 photon. And we want to find a way to fix the coefficients. And happily, because of this n equal to 2 supersymmetry, we have that these functions are holomorphic. This is this prepotential, f of a. And we used this to the most crazy extent we could, yes? And this also defines the metric for this sigma model. One magical thing was this coordinate transformation, or the definition of what is the dual variables. And this definition allowed us to see explicitly the S-duality. So our theory, we showed that it has S-duality both at the level of the path integral and at the level of the Dion spectrum. And this is why then Seiberg and Witten started saying, oh, something is happening here. We have this symmetry. There is also the shift of the theta uncle by 2 pi, but this is a trivial symmetry. Combining them, we have the full SL to Z. And in some sense already, because you have this SL to Z, you say, I have a torus, right? Good. And then we set up this problem. All we knew at the beginning in our lives was the weak coupling, because that's the only thing we knew before. We only knew to know how to do one loop calculation. So we went along with our one loop thing, and we saw that there is a monodromy. We saw that the functions are multivalued, A and AD. So if a cat comes out, it has to go somewhere. And we followed, we tried to say, oh, is it possible that there are 2 singularities? Oh, no, it's not. Oh, is it possible that there is 3? Oh, yes. I mean, it's like this. So with all of these intelligent assumptions, we found a way to say, oh, for these 3 singularities assumption now, I can find the solution. And what was really crucial, and this you should never forget in your life, we made a further assumption that the mass of the monopole goes to 0 on the one of them. And why this is, can you tell me the slogan? If it blows up in your face, you did something wrong. Yes? What does it mean that you did something wrong from the point of view of an effective field theory? You integrated out a massive particle, a massless particle. So in a generic point of the moduli space, the particle was massive, but it so happens that in this whatever point, it becomes massless. And this was an illegal thing. That's why it blew up in your face. And this is why it makes sense to say, oh, let's study what happens when the monopole becomes massless. So we went along with that. We wrote something down. By the way, what does it mean that the monopole is massless? It means that we have to go to dual coordinates, where we have a dual photon and a dual electron that are weakly coupled, so weakly coupled electromagnetism. We wrote down what this means. We did the singularities. We patched all three of them, and then we had a very concrete mathematical problem, this A and AD, with these three very specific singularities. And we put them together in this Riemann-Hilbert problem that I described here with this curve. And we solved. And we also we did this check, good. We did this check, good, and this is also nice. You learn a little bit how to do these calculations. Very similarly, you can do this calculation, and if you want to be lazy, you can copy my notes. And then, of course, the next steps in life is what happens if you have a UN. What happens? Can you guess? Yes. I mean, I can tell you a picture, which is very nice. So we had two guys. Let's say it says U3. You will have three guys. And you will have whatever, your cats. And so on. So you will have a torus with two holes. SUN, you know, the genus goes up. So this is why this thing is nice with the pictures. What happens when you have hypers? Okay, there is no way to check, but there are extra poles that you can get here. And then once you understand that the hyper is a pole, you are very happy and you go and you basically can immediately write down things. Yes, and my advice, if you like this, is to read also this very beautiful paper by Witten, where he derives this from M theory. And then you will be so happy. Yeah, anyway, yeah, I think that's it, yes. Have fun.